you, Rajesh. It's a real pleasure to have this meeting hosted by ICTS. It was originally intended, obviously, to be in person, but hopefully this will be a nice meeting nonetheless. And in the future, we will have an in-person meeting, I'm sure. So our first speaker of the meeting will be David Schaich from the University of Liverpool. So please, David, do start.
Yeah, I'll get underway just a few minutes ahead of schedule while we deal with all the getting set up bits. And in addition to echoing Toby's remarks that we hope to be meeting in person in the future, I also want to start by thanking the ICTS staff for making this online encounter possible. It's good to have at least something coming out of our original plans of hosting an in-person meeting at this time. And I should also, just as some additional background, mention that the in-person program was originally scheduled to be 10 full days, combining in roughly equal proportion pedagogical background and lectures, and then cutting-edge research discussions. And we've, due to the time zone issues that Rajesh mentioned, those 10 full days have been cut down into 11 presentations and discussions, of which this is the first one, where I will still be trying to balance pedagogy on the one hand and ongoing research on the other, but this is obviously more constrained and more limited than we hope to be able to get back to as soon as we can. I will also say, just for more logistics, I'm going to assume that the slides are showing okay. We tested that a bit earlier, and that I am audible and that the connection is stable. So speak up if there are any issues about any of that. I'll also not be monitoring the chat window. I'll rely on Toby to keep an eye on that and let me know if there's anything in there I need to discuss. So the topic I will be discussing is lattice supersymmetry, taking sort of a broad view of this field and emphasizing the significant progress that is currently being made in a large number of areas and directions under the overall umbrella of supersymmetric quantum field theories investigated through the techniques of lattice field theory. So the plan, after motivating why we want to use lattice techniques to look at supersymmetric theories, I'll quickly go through a broader overview of what I call special cases, for reasons we'll see, that I don't do much work on myself. And then transitioning from that more background overview to the research that I work on, the big portion of the talk will be presenting maximally supersymmetric Yang-Mills theories, some brief highlights of the lattice formulation that we use to study those, and then some results both in 2- and 3-dimensional dimensionally reduced thermodynamics with 16 supercharges, and then the full 4-dimensional N=4 super Yang-Mills theory, looking in particular at its static potential and scaling dimensions, and then to the extent time remains, looking at some of the future directions that are compelling to pursue in lattice supersymmetry. And I'll say before I get going that these slides are online at that link, which I should have pasted into the chat window before getting going. And I also want to encourage interaction even as I go through this presentation, rather than postponing everything to the scheduled discussion session that we have afterwards. The point of getting us all together here and now on this same Zoom channel is to enable these sorts of interactions, which will also be hopefully helpful to those who, due to reasons of time or conflicts, will be listening to this recording online after the fact. Now, the journey of 1,000 miles, as they say, begins with asking, is it worth it? And I think there are many distinct directions that compellingly motivate using lattice field theory to investigate supersymmetric theories. What lattice field theory does is that it promises non-perturbative predictions from first principles for these systems, which are relevant in at least the 3 areas I highlight here. Of course, supersymmetric extensions of the standard model that are currently being searched for at ongoing and future collider experiments are how supersymmetry is most famous among the general population. And all of those sorts of setups rely, well, typically on a non-perturbative dynamical supersymmetry breaking process that requires some of the first principles investigations that lattice field theory enables. More generally, being able to non-perturbatively investigate quantum field theories is necessary to really understand how they behave. And details like the structure of the vacuum, non-perturbative confinement phase transitions, conformality, and all sorts of other complicated non-perturbative aspects of quantum field theory can be investigated using lattice techniques and also benefit from the simplifications of supersymmetry, which has allowed a lot of analytic progress to be made over the past few decades in the context of things like electric magnetic dualities and understanding of conformality and confinement. And speaking of dualities, of course, there's the holographic or ADS-CFT gauge gravity duality that relates exactly these supersymmetric quantum field theories to stringy theories of gravity in a different number of dimensions. And that is going to be the direction I focus on most today, as it's the best aligned with the themes of this program, and I suspect the interests of the participants. Now, to give some background very briefly on lattice field theory, if we recall the path integral formulation of a quantum field theory, formally we can express any given operator as this path integral of that operator evaluated on field configurations that I represent by this capital phi, weighted by the exponential of the action of phi, where there's a negative sign there instead of an imaginary unit, because I have taken the step of Wick rotating to Euclidean space just as a starting point. The downside to this formal definition is that these infinite dimensional integrals over all values of all fields at all points in space and time are in general intractable, except in very extremely simple special cases. And we have to regularize this path integral, which the lattice formulation does, by defining the theory in a finite discrete space-time illustrated here, where nearest neighboring sites are separated by some non-zero distance labeled A, and the total size of the system is the number of those sites times the separation gives this capital L. And compared to other regularizations like dimensional regularization, lattice field theory has several important advantages or strengths: that it is completely gauge invariant. There's no need to gauge fix, deal with ghosts, any of that. It's completely non-perturbative and is defined directly in the number of dimensions of interest, with no need to generalize the definition of your gamma 5 away from integer number dimensions, for example. It's not so different from the naive cutoff regularization that you may have encountered in an introductory quantum field theory course. This non-zero lattice spacing between nearest neighboring sites introduces an effective UV cutoff scale, just as the inverse of that length. And the process of removing this cutoff corresponds to what is called the continuum limit, where the spacing between lattice sites goes to 0, while at the same time we increase the number of lattice sites so that we retain a non-zero size of the space-time that we are formulating. Where lattice field theory is better than just a naive momentum cutoff is that it preserves a subset of the continuous space-time symmetries. Lorentz translations and boosts give the Poincare group. A hypercubic remnant of that is preserved through this lattice setup, assuming a sufficiently regular lattice structure, which I will assume. And it turns out that a hypercubic lattice, for example, has a sufficient amount of discrete symmetry to guarantee that continuous Poincare symmetry is automatically restored as we remove this cutoff by taking the continuum limit, which I go through that in some detail because it will play a role later in this presentation. And lattice field theory also, by formulating the system as a finite number of degrees of freedom, also allows us to carry out numerical calculations of these regularized field theory on finite computers, which these days are large and powerful enough to allow us to evaluate systems with up to 1 billion degrees of freedom in that path integral, where the fermion operator is represented now as a sort of billion by billion matrix that we have to manipulate. This is still a very challenging way of doing things. And I'll call it the main way that this is carried out is through a generic set of computational algorithms that are called importance sampling Monte Carlo, which have the feature that these algorithms sample the field configurations weighted with the appropriate probability that appears in that path integral, this e to the minus s over the partition function, so that the formal expression for an observable just collapses to this average over the evaluation of that observable on some number of independent field configurations where the statistical uncertainty decreases with the square root of the number of independent configurations you are able to sample with your algorithm. Now, as far as I'm concerned, this is all great, but there is a problem when we come to supersymmetry, which has been a sticking point for many years. Essentially, supersymmetry must be broken on the lattice simply because it is a space-time symmetry generalizing that Poincare symmetry I mentioned through the addition of these spinor operators Q and Q bar, somewhere between 1 to n of those, where this calligraphic n is the first of several n's that I will try to keep clear in the presentation. Now, the super Poincare algebra, for those who aren't familiar, it contains anti-commutators of this sort, where 2 of these supersymmetry generators anti-commute to form a infinitesimal translation, or a generator thereof, which is simply broken in a lattice space-time where we do not have infinitesimal translations. And breaking supersymmetry at the classical level in this way then allows all possible supersymmetry violating operators to be generated by quantum effects in the course of a lattice quantum field theory calculation. And many of these are relevant operators that then need to be fine-tuned away through the addition and tuning of counterterms, especially looking at the scalar sector, where we have scalar mass terms like the Higgs mass in the standard model, Yukawa couplings, 4 scalar quartic operators, as well as fermion masses for both quarks, if we have those, and gluinos, the superpartner of the gauge bosons, the gluons. Where progress is being made in recent years is by simplifying this enormous fine-tuning challenge in one of at least these 3 ways, which I highlight these 3 because they are how the remainder of this presentation will be organized. First, we can avoid scalars entirely and get rid of a lot of the fine-tuning challenge just by reducing the number of operators we have to deal with. We can also reduce dimensions, make things super renormalizable, simplify them in that way. Or, and this will be the bulk of the n equal 4 super Yang-Mills part, we can maximize the symmetries in such a way that we can preserve some subset of them, even at non-zero lattice spacing. And I'm going to go back to this outline frequently as we go through this talk, just to remind myself to pause on occasion and check in if there are any questions about what we just saw. And if you know to expect this at the end of each section, I won't spend too much time on this screen. I will just charge ahead to first now, there's 2 special cases that I mentioned on the previous slides, avoiding, I see there is a raised hand, so if there's a question, let's do that now before I go on?
You might have to unmute to ask your question.
Which I hope is possible for participants to unmute themselves.
Sir, I have a question.
Go ahead.
Yeah, sir, so in lattice, you told us that in lattice field theory, you are considering Euclidean spacetime. So
Right.
Considering non-Euclidean geometry of the spacetime, will the Lorentz invariance still hold?
So Lorentz invariance is something that we're going to get from Minkowski spacetime, which differs from Euclidean only by a Wick rotation. And that does have important consequences that lattice field theory then only is accessing essentially static equilibrium properties. And we might hear from Shailesh Chandrasekaran later today about non-equilibrium properties where that rotation between Minkowski and Euclidean space is more complicated. If we go away even from Minkowski and Euclidean space and start thinking about curved spacetimes, then things become much more challenging. Maybe in the discussion, Rich Brower can tell us about that if we have time, but I don't want to get into it now. And the challenge there has to do with the automatic recovery of symmetries, which relies on the regular lattice structure and becomes much more complicated if there is any curvature in the game. So for lattice field theory in general, and this talk in particular, it will be all entirely on flat spacetimes with the idea that we can freely rotate equilibrium properties between Minkowski and Euclidean signatures.
Yeah, so my question was that you said that on the lattice, the problem is, you couldn't talk about infinitesimal translations. And that is why the supersymmetry realization is not possible. But the thing is, then the next statement you made is that, okay, let us reduce the number of scalars, let us reduce the number of dimensions. How is that basically going to help you in realizing something infinitesimal? And the second question was, how about like on the lattice, if you cannot realize a translational operator, obviously you'll not be able to realize a rotational operator. So how do you talk about spin, etc.?
Yeah, so we do still have translations and rotations on the lattice. They are just discrete translations by this finite lattice spacing or discrete rotations by, say, 90 degrees in all 4 or however many space-time dimensions you have. And the fact that these discrete transformations automatically reproduce the continuous symmetries when you remove this regulator is indeed the answer to that second question. How do you talk about spin and so on? You take the continuum limit, these discrete symmetries generalize to the full continuous symmetries that you started off with in the theory you're targeting. And for the first question, how these simplifications help us, that is exactly the topic of the next few sections. So I think I should go on to those, and if that assistance is not clear, then we can revisit that question. So let me do that now and talk about n=1 super-Yang middles, something that I have not worked on myself. But as I mentioned earlier, this is just an SUN gauge theory with a single superpartner for that gauge field, a massless Majorana fermion in the adjoint representation. So there are no quarks whose masses we would have to tune. There are no 4 scalar operators, Yukawa, or scalar mass terms. The only fine-tuning that we would have left is, at most, this gluino mass, the mass of this fermion superpartner of the gauge field, the gluon. And here we have 2 options. So some lattice background that I'm not going to get into in any detail is that straightforward lattice fermion formulations, like those initially developed by Wilson, they explicitly break the chiral symmetry that otherwise would protect the mass of this, or forbid, rather, the mass of this gluino, in much the same way that the different chiral symmetry of QCD has that same effect of protecting the masses of the quarks. And with this explicit breaking of chiral symmetry, large additive mass renormalization for this gluino becomes inevitable in a quantum field theory calculation, and that is exactly what has to be fine-tuned. There are formulations of fermions in a discrete lattice spacetime that preserve some form of chiral symmetry. These go by the name of overlap fermions and domain wall fermions. The downside here is that these fermion formulations, when we're doing numerical computations, they are much more expensive than the straightforward option. And both of these options are being explored in lattice investigations of n equal 1 super Yang Mills, going on with a broken chiral symmetry in your formulation and fine-tuning that gluino mass, where supersymmetry is only recovered as we take not only the continuum limit, but also the chiral limits of tuning that mass to 0, as well as looking at domain wall or overlap fermions, where this gluino mass operator is forbidden by that chiral symmetry, so that in the continuum limit, supersymmetry emerges automatically as an accidental symmetry. Some of the results that have come out pretty recently, just in the past year, here we're looking at masses of composite particles in n equal 1 super Yang Mills, comparing in particular a scalar, a pseudoscalar, and their fermionic partner, which in theory are all supposed to form a mass degenerate supermultiplet. This is taking the approach of breaking chiral symmetry and fine-tuning away that large additive mass renormalization, and the horizontal axis on these plots is indeed a measure of how large that gluino mass is, with the massless limit being the left-hand side. And on the vertical axis, we have the masses of these composite particles, which we can see are approaching degeneracy in the chiral limit, with that degeneracy becoming better and better as we approach the continuum limit, where supersymmetry should be restored, and which corresponds in this language to increasing the value of beta, the inverse gauge coupling in lattice terms. So this, on the left plot, we have a relatively coarse lattice with a relatively large lattice spacing, whereas on the right, the lattice spacing has become finer. We've moved closer to the continuum limit, and we're seeing better degeneracy within this supermultiplet. I got a flash about another raised hand, so I'll pause if there's something specific about this slide.
Yeah, no, but why do you once you invoke the lattice, do you break chirality? Does the gamma operator stop existing, or what has happened then?
So essentially, it's much the same issue as the complications generalizing chirality in that gamma 5 away from an integer number of dimensions. Just that once you have a discrete space-time, the concept of chirality can be tricky to realize. And probably the best answer to this is directing you to some of the literature on domain wall and overlap fermions, which as I said, I'm not going to get into those lattice details here and now. There are many good reviews that we can pull up after the fact. The way that these domain wall or overlap fermions work is that they essentially redefine the notion of chirality on the lattice to obey a relation known as the Ginzburg-Wilson relation that came about, I think, in 1982, and showed the remnant of chirality that you can define on a discrete spacetime. But it is indeed the fact that spacetime is discretized that leads to this problem with chirality and can be cleverly addressed through these Ginzburg-Wilson fermions. But as it suggests to go back to 1982 to discuss this, there's a very long story, which is why I'm pushing that sort of toward the background and asking you to take it as given for the purpose of this talk, that this sort of thing can be done, and then we can look into it in more detail afterwards. And I will go on with additional work by the same German collaboration, looking more directly at the restoration of supersymmetry in the continuum limit. So this is seeing a consequence of supersymmetry would be these degenerate supermultiplets. So seeing them form is a promising sign, but not a guarantee that they are forming due to supersymmetry. A much better sign of that is measuring word identities of the supersymmetry transformation, which quantify the extent to which the supersymmetry is broken by working on a finite space-time. And the reference here from last March goes into the definition of what word identities are being computed and how they're defined on the lattice, which is also a non-trivial aspect of this. The result, though, is that these points come out of the calculation. So they are measuring the violation of supersymmetry at the horizontal axis is now a measure of the lattice spacing that we know is breaking supersymmetry, and extrapolating to a vanishing lattice spacing gets or produces a continuum limit result that is consistent within its error bars with the restoration of supersymmetry, these word identities being satisfied. And in particular, the lattice formulation of the gluinos being used here, which is what's known as the Clover-Wilson action. This is set up in such a way that the discretization effects breaking supersymmetry are expected to depend quadratically on the lattice spacing. And with the lattice spacing squared on the horizontal axis here, we can see a almost perfect lineup with that quadratic expectation, a sign of things behaving as advertised with the restoration of supersymmetry as we take the chiral continuum limit, despite having chiral symmetry and supersymmetry both being broken in these calculations. Another group doing similar work is based in Jena, using a different lattice action with what is called a twisted mass rather than a Clover term. And the motivation for this is that this twisted mass action provides an extra parameter that we can tune, which at first sounds like exactly what we wanted to get away from, making things more complicated by adding more parameters. The point here is that by tuning the so-called twist angle, that approach to the continuum limit should become better controlled and less sensitive to a non-zero lattice spacing. And from this paper from October, I'm just showing here an illustration of how that works, looking at the scalar and pseudoscalar partners that were two of the three composite states in that supermultiplet we looked at a couple of slides ago, and seeing how as the twist angle is turned on and increased, the degeneracy of these two states can be improved if the angle is tuned to an appropriate value, where here 45 degrees pi over 4 was just chosen as the simplest possible value, where there's much better agreement even at the same value of the lattice spacing and this additively renormalized gluino mass rather far from zero. And turning now to just one bit about the overlap formulation, I've already said quite a bit about overlap in domain wall fermions. The issue here with the overlap formulation and what makes it so expensive is the need to compute the sign of the fermion operator, which you should remember is a very large sparse matrix, roughly 1 billion by 1 billion, producing more matrix elements than you can really store on any reasonable computer. So computing the sign function for that huge billion by billion matrix is the big challenge of overlap lattice calculations. And in this work from May, an nth order polynomial is being used to approximate that sign function, where the chiral limit of a massless gluino corresponds to the limit of this order n being taken to infinity. What's plotted here is the bare gluino condensate from 12 to the 4th lattices plotted against the inverse of the order of that polynomial. And the key here is that even though a finite polynomial approximation to compute this sign results in some residual chiral symmetry breaking, the chiral symmetry of overlap fermions is still good enough that there are only multiplicative renormalizations, both in the gluino mass and in the chiral condensate. So if the bare gluino mass is set to 0, that is multiplicatively renormalized still to 0. And this is essentially restarting this line of work on the overlap or domain wall fermion approach to n=1 super Yang middles, which I know Rich Brower is on the call. He, Simon Catterall, Joel Geet, and a few others looked at this more than a decade ago. And this is the first resumption of that work, which I'm very excited to see getting back in gear. And moving straight on to that other simplification that I mentioned, how we can simplify systems by reducing dimensions. Let's just go straight ahead to the ultimate simplification that we can do in this manner, which is to compactify all the spatial dimensions of our theory down to a single point so that we are working with a quantum mechanical system rather than a quantum field theory of a balanced set of bosonic and fermionic matrices interacting with each other as they evolve through time, where these are n by n matrices, where this n, different from the calligraphic n, comes from the rank of the gauge group that we started off with in either 4 or 10 dimensions. And this system is actually simple enough that a lattice discretization of the only remaining time dimension is not even strictly necessary. It's possible to numerically analyze these theories with non-lattice approaches, where I saw Masanori Hanada on the meeting earlier, and he's done a lot of work on that, some of which we will see soon. And Jun Nishimura is going to give a whole presentation on the topic of matrix models tomorrow. So I'm only going to flash a couple of results here before moving on, focusing on the maximally supersymmetric theory with 16 supercharges that is motivated by a still remaining holographic connection where the thermodynamics of this maximal super Yang mills, even reduced to 0 + 1 dimensions, is supposed to exhibit behavior equivalent to black holes in string theory. Now, I would say the best demonstration of this to date is in this work from a few years ago by the Monte Carlo string M theory collaboration that Masanori is a part of, where a very careful set of extrapolations, both to a continuum limit, an infinite number of lattice sites in that discretized time direction, as well as a large n limit in the number of colors, were carried out to provide non-perturbative numerical predictions for the internal energy of the black hole dual to this finite temperature quantum mechanical system, where the extrapolations are shown on the left, and they produce, this whole plot here produces, I believe, the second point at a temperature of 0.5 on the right-hand plot, where repeating these extrapolations for various different temperatures shows both that the non-perturbative numerical predictions are approaching the leading order expectation from supergravity, the solid black line, as the temperature becomes sufficiently low. And the deviations from that leading order prediction are then numerical lattice predictions for the higher order corrections to that supergravity result, which can be determined from a fit to the data, with several different fits being shown how they improve as additional corrections are added. One nice aspect of the code that was used for this work is that because the number of colors is so high, they're looking at SUN gauge theories up to SU32, they actually parallelize the individual n by n matrices being manipulated here and spread those across multiple computing cores. Some more recent work, in fact, as yet unpublished and still being finalized to pop on the archive in the next month or so, is something that I've been doing with Raghav Jha and Anosh Joseph, which is adding a deformation to this maximally supersymmetric quantum mechanics that still deforms the theory while preserving all of its supercharges in the continuum formulation by Berenstein, Maldacena, and Nastase close to 20 years ago now. And what this deformation does is introduce an effective mass term and providing a more interesting space of behavior and phenomena to investigate, where we have multiple parameters in the parameter space in the phase diagram, and there is in fact known to be a deconfinement transition, or let me just call it a phase transition, that has been investigated both in holography, in the large N strong coupling limit, which produces this red line as the prediction for the critical temperature normalized by this mass deformation parameter mu, and also investigated perturbatively in the perturbative limit of a weak coupling G, which is shown here on the horizontal axis in logarithmic units. So this is a semi-log plot showing both perturbative expectations, a leading order holographic prediction, and some preliminary numerical results that are matching the perturbative expectations at weak coupling, and then beginning to move up towards that holographic expectation at stronger couplings, with a fixed number of colors of 12, which may or may not be large enough to fully reproduce that large N holographic limit. And those are the only things I'm going to say about those two special cases. And we did have some questions about chiral fermions, the overlap formulation, while going through it. So I will just pause for only a second or two here to see if there are any more before going into the more research-focused rather than broad, detail-free overview part of the talk. Now, the idea of the work I've been doing with Toby, with Anosh, Raghav, Simon Catterall, and several others over the years is to preserve a subalgebra of the supersymmetries, even in the discrete spacetime of the lattice. And this, an exact analogy to the recovery of continuous rotational and translational symmetries of ordinary lattice field theory. This turns out to guarantee that the correct fully supersymmetric continuum limit with all 16 supersymmetries can easily be obtained with little or no fine-tuning in a way that I think I don't have time to go into the details here unless there are questions about them, but it's exactly analogous to the recovery of rotational invariance. This idea was discovered initially or constructed initially in two different ways, one coming from topological field theory and using the idea of topological twisting, the other coming from a background of orbifolded dimensional deconstruction. Both of those approaches were shown to produce the equivalent outcome, and there's a nice review from about a decade ago explaining how that all goes through. One of the consequences of this is that a large number of supersymmetries are needed in order to be able to preserve any one of them. So a minimum of 2 to the power d supersymmetries are needed for this approach in d dimensions, so that when we look at 4 space-time dimensions, the only unique theory where we are able to carry out this procedure is indeed n equal 4 super Yang-Mills. I'm expecting that n equal 4 super Yang-Mills is quite familiar, so to this audience, I'll just remind you that it's an SUN gauge theory with 4 fermions and 6 scalars, all of which are part of the same supermultiplet. They're all massless and transform the adjoint representation. And the symmetries of this theory make it arguably the simplest non-trivial quantum field theory in 4 dimensions. Of course, we have the 16 supersymmetries, which also transform under a global R symmetry or flavor symmetry that I can go back and forth between calling that an SU4 or an SO6. The details of that relation are not going to matter for the work at hand. And they're also conformal symmetries. The theory is scale invariant and its beta function is exactly 0 for all values of its 't Hooft coupling. The symmetries here are sufficient that this 't Hooft coupling lambda and the rank of the gauge theory are the only remaining parameters. All of the usual kinetic, Yukawa, and quartic terms that pop up in the action of the theory are related by those symmetries, leaving only those 2 parameters in the formulation. I'm going to go through the basic idea of the topological twisting construction of the supersymmetric lattice theory that I mentioned on the previous slide. And to do that quickly, the way I like to think about this is with the intuitive picture of taking the 16 supersymmetries of n equal 4 super Yang-Mills and placing them in a 4x4 matrix shown here, whereas I go along each row, the R symmetry index of the supersymmetry is changing. That's the superscript here. And while I go down each column, the Lorentz index, which is an SO4 rotational symmetry in Euclidean spacetime, that alpha and alpha dot are what are changing. And given a 4x4 matrix, it's a knee-jerk reaction to expand it in a basis of gamma matrices, which are producing these calligraphic supersymmetries, calligraphic Q supersymmetries, that we can further repackage for reasons that will become clear in future slides into objects with indices running from 1 to 5. So a twisted scalar, a 5-component twisted vector, and a 10-component 2-index antisymmetric tensor, where I'm calling these twisted because this procedure of expanding the matrix in this way is effectively expressing these supersymmetries, organizing them in representations of a so-called twisted rotation group, which takes that SO4 Euclidean rotation group of the Lorentz symmetry and looks at the diagonal subgroup of its direct product with the SO4 subgroup of the full SO6 R symmetry. And in flat space, which is the only place we're going to be for this presentation, this procedure is just a change of variables that lets us work with calligraphic twisted supersymmetries that transform with an integer spin under this twisted rotation group. And as the question came up earlier, I should emphasize here that this is all being done in the continuum at this point. And still in the continuum, well, let me just forecast the idea. This twisting procedure was developed initially by Witten with the goal of seeing how much global supersymmetry could be preserved in curved spacetimes. And the strength of this change of variables is that the twisted scalar supersymmetry Q is nilpotent, so that there is a closed supersymmetry subalgebra, which is simply that Q anti-commuting with itself vanishes. And the qualitative hand-waving idea here, I said earlier that anti-commutators of this sort should be giving infinitesimal translations. Effectively, what is going on is that we have found the linear combination of those infinitesimal translations that loop back around to their starting point, so that the translation itself is simply that point and can be taken to that point, even in a curved or a discrete spacetime. We also, of course, have to carry out this change of variables self-consistently throughout the entire theory, so the fields also have to be recast in a way in these representations of the twisted rotation group. Those 4 fermion fields get recast into exactly the same form as the supersymmetries themselves. There are 16 components here that go to a 1 plus 5 plus 10. And the gauge field plus the 6 scalars get wrapped up into a complexified 5-component gauge field, where the complexification has the consequence that the gauge invariance is enhanced from SUN to a full UN gauge group. At the continuum, this is essentially irrelevant, since the U1 factor can be freely disregarded. In lattice calculations, we will see it has some non-trivial consequences. And with the theory fully reformulated in this way, it's simple to check that the twisted scalar supersymmetry interchanges bosonic and fermionic degrees of freedom. For example, acting on the complexified gauge field, we get a fermion out. And if we act twice with the supersymmetry on any field, it vanishes. So acting on that side gives us 0. Similarly for the other 2 rows there. Now, although we are working with 5-component objects, I skipped a slide in my mind. With the theory set up in this way, it is in fact almost trivial to go from the continuous spacetime to lattice spacetime. The lattice theory is nearly the same, even though 15 of the 16 supersymmetries are broken by a non-zero lattice spacing. All we have to do is replace the gauge covariant derivatives with finite difference operators and replace the complexified gauge field with what are called gauge links, where in contrast to QCD, if there are any QCD practitioners on this in this meeting, these gauge links are transforming in the algebra rather than the group, and that is necessary in order to maintain the supersymmetry. Because the fermions psi live in the algebra, so do the gauge links that are related to them by the supersymmetry. And the supersymmetric lattice action then follows, well, the full lattice action has this form. I won't go through those details because in the interest of time, but because Q squared acting on all fields vanishes, this first set of terms would vanish when we act with Q on the action. The last term vanishes due to a Bianchi identity that remains exact in lattice space-time, so we have a supersymmetric lattice action. We also have 5-component objects while we are still in 4-dimensional space-time, which implies that the lattice structure we have to use in these calculations is the so-called A4 star lattice, which is a 4-dimensional analog of the 2-dimensional triangular lattice pictured here, where 5 basis vectors are symmetrically spanning 4 space-time dimensions, with the consequence that they are linearly dependent and non-orthogonal. And the reason we have to set things up in this way is that the lattice fields are transforming in representations of the S5 point group symmetry of the A4 star lattice. In the two-dimensional triangular lattice, that's an S3 symmetry. Going up to 4 dimensions, we get S5, and these representations precisely match onto the representations of the continuous twisted rotation symmetry that we want to get in the continuum limit. Or this is the reason why we automatically recover that continuous rotational symmetry in the continuum limit. And it is exactly that restoration of rotational invariance that promotes the single preserved supercharge to restoring all the other 15. Now, because there are so many symmetries in this system, an exact UN gauge invariance, one exact supersymmetry, and then the S5 point group symmetry that corresponds to the continuous twisted rotation group, there were, before I got involved in this line of research, several analytic investigations that were able to prove several important results that the moduli space of the lattice theory is preserved to all orders in lattice perturbation theory, just like the continuum theory. The lattice beta function computed to one loop in lattice perturbation theory also vanishes. And there is at most one logarithmic tuning required in order to recover the full SO4 twisted rotation group in the continuum limit and thereby recover those full supersymmetries. My personal interest is in the numerical calculations or numerical analysis of this lattice theory, where the formulation that we've seen so far is not yet practical. Excuse me. We need to regulate zero modes and flat directions in order to be able to carry out numerical calculations. And these are especially tricky in that U1 sector that does not decouple at non-zero lattice spacing. Lifting flat directions in the SUN sector is quite easy. We just deform the theory by including a scalar potential of this form, which softly breaks that one remaining supersymmetry, the calligraphic Q. So we do have Q violating operators appearing in calculations, but because this is a soft breaking, we are guaranteed that those vanish when the tunable coefficient mu squared on this scalar potential is extrapolated to 0, which is what is shown in this plot, where a bunch of independent numerical lattice calculations are carried out to measure violations of a word identity of the scalar supersymmetry. The vertical axis here is measuring the relative violation of that word identity, and the violations are going exactly to 0 as mu squared goes to 0. For the U1 sector, we had to be a bit more clever and a bit more careful, and we lift the zero modes and flat directions in the U1 sector by supersymmetrically deforming the moduli space of the bosonic auxiliary field of the theory with a term that depends on the determinant of the plaquette, where the plaquette is the product of gauge lengths around the simplest possible face in the lattice, just a simple square. The determinant of that plaquette is the simplest non-trivial quantity sensitive to the U1 sector, and by constraining it, in particular doing it in a supersymmetric way, we are able to significantly reduce the violations of these ward identities compared to earlier work in red, where this sort of term was just added as another soft supersymmetry breaking deformation. This plot here is on a log-log axis, so that the blue line corresponds to these lattice artifacts vanishing, again, proportionally to a squared, just like the Clover action that we saw in the n=1 Super-Yang-Mills case. Now, the resulting lattice action that we end up with after taking those steps necessary to carry out calculations is relatively complicated. And to reduce the barriers to entry to this field for those who are curious in getting involved, our high-performance parallel code is publicly developed and released on GitHub with a user guide on the archive a few years ago, which is overdue for an update that should be coming as soon as we can get around to it. And I'm going to pause here and say that I know the time scheduled for the presentation is running out. I'm planning to take up some portion of the time allocated for discussion, since we have had some discussion already as I've been going through these slides, and I'll leave it to Toby to tell me when to wrap up. I can skip some or all of the remaining topics or circle back to them in that formal discussion as the interests of all of us guide us.
Well, David, shall we say 12 UK time? Is that good? Another 5 minutes?
Let's do 10 and see how close I can get there.
Okay. Well, how about 7, and then maybe there'll be some follow-up questions where we can discuss things that weren't covered in more detail.
You're the boss, so I will do as you say, and I'll follow your judgment on when to wrap up. So I can now, having gone through that lengthy formulation, we can look at some actual numerical results. First, continuing to simplify the theory by looking at dimensionally reduced systems down in 2 and 3 dimensions, and doing the same sort of calculation of thermodynamic properties that we saw in the quantum mechanical case. So here, our theory in 2 dimensions, once we dimensionally reduce, we have a 2D n=8,8 Super-Yang-Mills defined on a torus of length RL in space times R beta in time, with 4 of these scalar supersymmetries, because in 2 dimensions, 2 to the power 2, we get 1 preserved supersymmetry for each 4 supercharges in the theory. Now, holographically, at low temperatures, there is a prediction that decreasing the spatial length of this torus leads us to a first-order phase transition between a D1 phase, describing a homogeneous black string that becomes unstable and transitions to a D0 phase, describing a localized black hole in a supergravity system, where the holographic dictionary relates that to what I'm going to call, with some abuse of terminology, spatial deconfinement, that is signaled by the behavior of the Wilson line in the lattice calculations. The Wilson line is just the holonomy along this periodic spatial dimension on this torus. Now, I want to emphasize that in the thermal direction, the system is always deconfined in order to have this holographic connection to the black hole system. These are the sorts of numerical results that come from the lattice calculation, the left-hand plot showing exactly the magnitude of that spatial Wilson line, where at high temperatures, which are small spatial extents of the torus in the temporal direction, at high temperatures, the Wilson line has a large magnitude. As the temperature decreases, the Wilson line shifts to smaller values. And we also see these values getting smaller and smaller as n is increased. The number of colors in this theory is increased from 6 to 9 to 12, taking that large n limit. And the susceptibility of the Wilson line shown in the right-hand plot is showing a peak, signaling a transition at precisely the temperature where this shift from small to large values is going on. And in each of these cases, we're comparing two different lattice sizes with a fixed so-called aspect ratio between the spatial and temporal extent of the lattice. Now, simply having seen a transition of some sort is useful, but not a guarantee that the holographic predictions are correct. We can get some more information by looking at that same internal energy of the dual black hole that I flashed for the quantum mechanical system in a previous section, where that's what's plotted here in systems that we expect to be in both the D0 on the left and D1 on the right phases. So the two things we can say about these plots are, first, that it's difficult to distinguish between the leading behavior from supergravity for these two phases. One predicts behavior proportional to the temperature cubed to the power 3.0. The other predicts behavior proportional to the temperature to the power 3.2. So we can't directly distinguish that we are going from the D1 to D0 phase in that transition we saw in the Polyakov loop, or the Wilson line, excuse me. What we can say is that our results are consistent with the behavior in both of these phases. So this does give us much more confidence that we are seeing the desired phase transition between these two D0 and D1 phases in the Polyakov loop. The resulting phase transition that the lattice calculations are producing is shown here, where the red and blue lines are expectations that were also shown on that previous cartoon, the red being that supergravity prediction for a low temperature first order transition, the blue coming from a supersymmetric bosonic quantum mechanics theory, where the high temperature is large enough that the fermions are essentially removed from the theory. So overall, our results are consistent with the expectations, in part because the error bars become larger and larger as we look at transitions at lower and lower temperatures. What will help there are a larger number of colors, larger lattice sizes, and controlled extrapolations. And one place where we have begun to carry out these controlled extrapolations are the similar investigations in the three-dimensional theory, which is much more recent work from a couple of months ago, where now looking at three-dimensional maximally supersymmetric Yang mills, we again approach the leading holographic expectation for a low temperature. That is this dotted line here in the left-hand plot, a power of t to the 10^3 in the three-dimensional case, whereas the solid line is the high temperature expectation that we move towards as the temperature increases. And what's shown on the right are some initial continuum extrapolations where we've now fixed the aspect ratio between the spatial and temporal sides of our three torus, and also fixed the gauge group, the number of colors, and seeing that we can control these extrapolations, though there are obviously still large uncertainties, as we saw earlier. So this is the current state of the art for these investigations, and will be probably the last very brief pause that I take to see if there are questions on that topic.
May I ask you one thing about so a little bit before black hole black string transition, and you say that you said error bar becomes big, and so agreement looks okay. But I thought maybe there's a sort of ambiguity about the location of a first order transition, because when you say first, so it's, I suppose this is a first order transition with some hysteresis. So probably by first order transition, you mean the point where free energy becomes the same value, but at the same time in simulation, maybe you are seeing the point where instability of each phase sets in. So maybe if you take into account that ambiguity, this can be a better agreement.
Yeah, that's that's not the source of the ambiguity here, since that first order transition is something that we only recover in the large N and low temperature limit.
Mm-hmm.
So what we really see at a, the relatively modest number of N from 6 to 12 here and the modest
Mm-hmm.
lattice sizes is always a continuous transition where the first order nature is actually something we can look at by fitting the growth of the susceptibility peak.
Yeah, but then the problem is probably this susceptibility captures not the point where free energy becomes the same, but the other two, I mean, instability sets in the confined phase or confined phase. That is probably picked up this susceptibility analysis. I think in terms of paper by Aharoni, Miwara, and collaborators, there are like a Gross-Witten-Wadia transition and Hagedorn transition, and also there is a point where free energy becomes the same. So there are three sort of transitions. I think this analysis captures probably Hagedorn transition or maybe Gross-Witten-Wadia transition, but not the point where free energy becomes the same, I think. But I'm not 100% sure, but that's possible. So maybe.
Yeah, we'll have to discuss that more offline, mm-hmm. Which is why it's a shame we can't all be in Bangalore together to do so.
Yeah, but I thought the agreement could be better than actually, we naively see from the plot. That was my, optimistic view.
Yeah, the way I would really check for a first order transition would be to compute the density of states, which I'm working on in simpler bosonic theories, where we can really see the phase coexistence that characterizes mm-hmm. a first order transition. Mm-hmm. That is very much work in progress, but we'll certainly address this issue.
Mm-hmm. Okay, thank you.
Thanks for that question, which is touching on an interesting aspect of these lattice phase diagrams that I'm admittedly going through quite quickly in the remaining few minutes. And given the small amount of time remaining, I will skip the static potential of n = 4 super Yang Mills, which is the first non-trivial thing that you, or that a lattice field theorist looks at in a given four-dimensional field theory. We have results that look like that, Coulombic, with a nice prediction for the Coulomb coefficient. What may be more interesting is looking at some of the scaling dimensions of these, this superconformal theory, where just as with the rotational symmetry, conformality is also broken by formulation on a finite discrete spacetime. There's a UV cutoff introduced by the lattice spacing. There's an IR cutoff introduced by the total extent of the lattice. So the extent to which we can compute scaling dimensions of conformal operators is a good test of, or the state of the art of lattice calculations. What I'm showing in this plot is on log-log axes. This is power law decay for a particular operator of n = 4 super Yang Mills, known as the Konishi operator. And the green line here is not a fit, but rather the perturbative expectation for this power law decay, given a perturbative computation of its scaling dimension, which is 2 plus this coupling-dependent anomalous dimension. One of the ways we can investigate anomalous dimensions on the lattice is by using the finite size of the lattice as a tool rather than a limitation. Monte Carlo renormalization group analysis is a classic way of doing that. Skipping over the details of how it works and just showing some of the results that we have, also ongoing work still to be published, able to reproduce the perturbative value for the full Konishi scaling dimension at weak coupling, with possible hints of deviation from that at stronger couplings, still very far from the maximum scaling dimension that is set by bootstrap analyses. I should also say some word of caution about the strong coupling results here, coming from work that is just about to appear on the archive later this month with Georg Bergner, where we look at a different scaling dimension using the eigenvalues of the fermion operator to predict the scaling dimension of the corresponding fermion bilinear. This is analogous to the mass anomalous dimension in non-supersymmetric field theories, which I know a lot of you have done a lot of work on over the years in the context of composite Higgs models. In N=4 Super-Yang-Mills, this anomalous dimension should be exactly zero. The scaling dimension of this fermion bilinear operator is protected, and by measuring the anomalous dimension on the lattice, we can see the extent to which the lattice spacing, the finite volume, the breaking of conformality is preventing us from measuring zero. And what's shown here is an effective scale-dependent anomalous dimension that should produce the true result of zero at sufficiently low energy scales, this omega squared energy parameter much less than 1, which we see is the case for many of the different couplings that we, or really all of the couplings we've analyzed are at least approaching zero. Once we get up to lambda of 2 or 2.5, the relatively strong coupling, the lattice effects are such that we need significantly larger lattice volumes than the 16 to the 4th lattice is considered here in order to really see something consistent with zero. And I also emphasize that this figure shows the free theory result on the 16 to the 4th A4 star lattice to show how the formulation of the theory on the lattice and the corresponding breaking of conformality produce a non-zero result for an anomalous dimension even in the free theory. So we can see the shape of these lattice artifacts and how much they depend on the coupling from 0 up toward 2. So that skips over the future directions on supersymmetric QCD and looking at sign problems, where we will have a chance to hear about sign problems in a couple of later talks by Schaich Chandrasekaran and Jun Nishimura. I will just wrap up there and sort of open the whole floor for the more freewheeling discussion that is not just me going through slides, but hearing hopefully from more of you about aspects of lattice field theory and lattice supersymmetry that interest you. So thanks for your attention. And what would you like to discuss next?
Well, I think we should thank David for a very nice talk. So thank you, David. I think firstly, before we go to sort of our potential discussion, we can see if there are any specific questions following up on the talk. So if you can't unmute, just say in the chat and we can try and unmute you. I can't see any particular questions, in which case we could have some more general questions or discussions. We have,
yes, we have
20 minutes or so.
More general question, as you said. In your beginning, you have said that you have some advance in to putting supersymmetric Young-Mills theory in the lattice. My question is going really to the physical part. Are there any physical results you obtain from all those procedures?
So by physical, I assume we're not talking about the real world physics where supersymmetry is not realized in the nature that we are living in and using to communicate with this talk. We know that supersymmetry as, let me go here to the motivation that if supersymmetry exists in nature, it must be broken at the low energies where we live. And my personal interests are more on the directions of using supersymmetry as a tool to learn more about the quantum field theories, or the general structure of quantum field theories that do govern the universe, as well as the holographic dualities that have been so important in recent years. Now, I can say that if we want to consider spontaneous supersymmetry breaking of the sort that could lead to some sort of supersymmetric extension of the standard model, there is an issue with that. So there has been investigations of dynamical supersymmetry breaking in a simplified system in order to have something that can be done with the technologies of, well, 6 years ago at this point. The issue with dynamical supersymmetry breaking is that it can only happen if what is called the Witten index vanishes, where so the Witten index equaling 0 is a necessary but not sufficient condition for spontaneous supersymmetry breaking of the sort envisioned in supersymmetric extensions of the standard model. And in the lattice formulation, the Witten index is just the partition function, so that when this vanishes as required for spontaneous supersymmetry breaking, we have an issue with importance sampling Monte Carlo that uses the partition function, or equivalently the action functional, to determine what configurations are the most important ones to sample. In particular, the only way to have a vanishing partition function from this path integral is to have a balanced number of positive and negative contributions from different field configurations, which is exactly what is called the sign problem that breaks down the most efficient and most powerful numerical techniques that we have to bring to bear on lattice field theories. And there have been some recent investigations by Anosh Joseph, just about 6 weeks, 2 months ago, looking at dynamical supersymmetry breaking in the supersymmetric quantum mechanics, again, a simplified system. And this is, I'm sure, will come up in some of those future talks that I highlighted. But if we want the predictions for LHC experiments coming out of this program, this is the sort of challenge we'll have to face. The focus of my work is on the more formal aspects of understanding quantum field theory itself as a domain of physics, as well as holographic dualities and the connection to quantum gravity in that same way.
I see, Costas, you have your hand up, is that right?
Yes. Hi, David, this was very nice talk.
Thank you.
Yeah, I have two related questions. So when you discussed it towards the end, the anomalous dimension for the Konishi, and you had the graph with the perturbative prediction, did this include, is this the prediction that comes from integrability or only from kind of low loop orders?
That's from the loop counting perturbation theory up to next to leading order.
Yeah, I mean, it would be interesting to put the integrability because, of course, the prediction.
My recollection is that the integrability result, while it's supposed to be valid for all Tuft couplings, does come from the planar limit and going to infinity. And there may be some deviations from that for the 2, 3, and 4 color theories we're looking at here. That's just my knee-jerk reaction rather than a specific objection.
Yeah. No, I mean, of course, it is true that n equals 2 is not large n, but it might move the curve in the right direction. That would be a kind of an indication. That's more common than anything else.
I should say, since I have the excuse, thanks for giving it to me. what we were hoping to see in a plot like this here for the Coulomb coefficient of the static potential, it has the same qualitative behavior, that there is agreement with perturbation theory, again, loop counting perturbation theory at weak coupling, and then things get a bit larger at strong coupling. We were hoping to see instead the opposite behavior of these results for the Coulomb coefficient turning over to the square root dependence predicted by some of the first ADS CFT calculations. And the fact that we're not seeing that here is probably suggesting that this deviation may well be as much due to these large lattice artifacts at strong coupling on the available lattice volumes as to physics. So I'm wary of providing or hoping too much for things like the integrability results to address this tension. I think this is additional systematic effects that are only partially accounted for in the error bars that we have in this work that is still being finalized.
And maybe a kind of related question, is there a hope to go beyond the Konishi to higher dimension unprotected operator?
Certainly we would like to do as much as we can. I think we're trying to take things one step at a time with the simplest things first, just making sure we can do those in a controlled way that is actually sensible. And I skipped over the discussion here that from the twisted formulation, there are indeed some complications even in the Konishi itself that have to do with how the representation of the twisted rotation group fits in with the R symmetry. And this shows up also in the Sugra, that the 20 prime operator with a protected scaling dimension. So while we have interest in getting as much as we can out of the lattice configurations that we're generating, which we will do some data release to make those publicly available for folks to look at and play with, there aren't immediate plans to go beyond the Konishi at this point. We're still wrestling with what we're seeing here.
Thank you.
Costas, was there a particular operator you had in mind that might be of interest?
I think integrability gives predictions for pretty much all of them. So in a sense, if you have more operators, you have a better chance to see this where the systematics lie. Just to give you another direction to study.
Which is a very good point, yeah. I'm sure there are also perturbative predictions for those as well.
Yeah, of course, the more you increase the size of the operator, the perturbative predictions become a bit harder, because the diagrams are going to involve kind of more loops just because you have more fields to contract. But the integrability should kind of do all of them pretty much on equal footing.
Yeah, maybe worth thinking about some targets to consider for next steps for exactly that purpose.
So also following up the comment you had about the supergravity ones, I mean, there was also some deviations. Are the deviations because of the reasons you just described about the kind of the U1 breaking? Yeah, this other graph, I think.
Well, this is
it? Not this one. I think you had two graphs, one with the blue line and one with the red line. Where was it? Yeah, here, this one.
Yeah.
Yeah.
So what I suspect is going on with, we see there's a nice agreement between the Konishi lattice data from, I think this is a 16 to the 4th lattice with gauge group U2. There's a limited range where we see a nice power law decay, where away, outside of that range, we're still sensitive to the scale of the lattice spacing, which is sitting right here at this first point. That is a correlator separated by a single lattice spacing, the UV cutoff scale. So it takes some time to, in the sort of Wilsonian RG sense, it takes some time to zoom out to low enough scales to see real physical behavior rather than a cutoff discrete lattice theory. And similarly, as we go to very large distances, which here I've cut things off at a distance about halfway across the lattice, where if we go beyond that, we would start being able to wrap around this hypertorus in different directions and would see a similar breakdown of that power law behavior. That was all prelude to say that the power law behavior for the Sugra operator here is obviously nowhere near as good in that same scaling range compared to the Konishi, where this black line is that protected scaling dimension of 2. What I suspect is going on there is just that the signal is so small, we're getting numerical accumulation of round-off effects when computing this correlator. You know, this 10 to the minus 8 is the limit of single precision. We are doing double precision calculations, but there's a lot of fluctuations and noise that is going into these calculations just by virtue of being based in stochastic analysis, importance sampling Monte Carlo. And I think that is why we're sort of seeing a leveling off or a plateau of the data at this level of a relatively small number. It's still a few orders of magnitude below the Konishi signal, but something that would need significantly more statistics to see if then things are better resolved at that point. That, though, is just my speculation and not something that I can say is certainly the issue of what's going on here. This particular point, I believe, is for this lambda lat of 0.5, where everything is behaving very well. When we do smarter approaches than just directly fitting this power law decay, doing a finite size scaling or Monte Carlo RG analysis that is better suited for the lattice setup.
And David, is the R here measured? Should I think of that as measured? Is it something like lattice spacings, or it's not exactly, is it?
There's an interesting story with that that I even skipped in the talk, which is the little box here mentions that for the static potential, I'm using a tree level improved analysis that significantly reduces discretization artifacts. So this is an indirect way of answering your question. What these two plots are showing data for the static potential measured with an R, which is just taking your basis vectors and figuring out the distance between the points at the end of them in the usual metric. The improved analysis, in contrast, identifies the distance R with the Fourier transform of the gluon propagator. That's just 1 over k squared. So the Fourier transform of that is related to 1 over r squared. This defines a sort of improved distance where plugging this improved distance into that same data from before gives the significantly improved behavior. The right-hand plot here is just unwrapping the Coulomb fit to show the fluctuations around each of the lines in the left-hand plot. So big fluctuations with the naive distance get smoothed out significantly with this improved distance, and that is another piece of work in progress for the Konishi operator. Here, we are still using the naive distance, add up all the displacements and figure out the length of that vector, and going to a tree level improved analysis, I'm hoping will also give us better behavior in this way. So a simple question that you asked with a long and sort of complicated answer behind it, going into some of the machinery of lattice calculations.
I guess we have a couple of minutes if there's one more comment or question.
We also had a good amount of discussion during the talk itself. So
if not, I suggest we thank David for his talk and for leading the discussion.